In this video, we will be going over how to use tree diagrams and tables as tools for finding sample spaces. Our learning objectives are to use tree diagrams to find sample spaces and compute probabilities, and then to use tables to find sample spaces and compute probabilities. So let's dive in. When we are working with theoretical probabilities, we know that we need to decide on the sample space for an event, and then find how many individual outcomes are in that event. We looked at some simple examples of this in an earlier section, the first section of Chapter 10, where we were looking at theoretical probabilities and exploring situations where you have a fixed number of outcomes and they're all equally likely. Things like flipping a coin, rolling a die, those sorts of things. For simple experiments, it's pretty easy to figure out what the sample space is. Again, the sample space is just all the possible outcomes in an experiment. But for more complicated situations, it can be a little trickier to figure out what the sample space is. And that's where tools like tree diagrams and tables come in handy. So a tree diagram, define that term here, is a diagram consisting of branches corresponding to outcomes of two or more probability experiments that are done in sequence. When constructing a tree diagram, we use branches emanating from a single point to show the outcomes for the first experiment. And then we add the outcomes for the second experiment using branches emanating from each branch that was used for the first experiment, and so on. Let's look at an example. We want to use a tree diagram to find the sample space for the sexes of 3 children in a family. Okay. So first of all, we've got the first child. And the first child could be either boy or girl. And then we've got the second child. And regardless of the sex of the first child, we've got the same 2 options for the second child, right? Either boy or girl. Boy, girl. And then we take that to another level for a third child, right? Where we put another set of branches coming off of each of these ones. Okay, so this is the set of branches for the first child. And then the second child. And then up here, third child. Okay. And if I trace through the branches, all the different pathways in this tree diagram, I end up with my sample space, all the possible outcomes. So we'd start at the top and just go through all the topmost branches. B, 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 or boy, boy, boy. Right, so that's one possibility, is 3 boys. Then you could have boy, boy, girl, right? 2 boys followed by a girl. Then I could have boy, girl, boy. Then I could have boy, girl, girl. All right, so these 4 possibilities are all the possible outcomes if the first child is a boy. Then we come down here and we consider the possibility of the first child being a girl. So we've got girl, boy, boy. Then we've got girl, boy, girl. Then I have girl, girl, boy. And then finally girl, girl, girl. Okay. So there are a total of 8 possible outcomes in my sample space, and the tree diagram was a tool that I used to figure out what that sample space looked like, right? And allowed me to list all the possible outcomes. Now that we have the sample space listed out here, we can use it to compute some probabilities. Let's look at example 2. If a family has 3 children, find the probability that they have at least one boy and one girl. Assume that each child is equally likely to be a boy or a girl. So in other words, what we're assuming is all 8 of the outcomes in this sample space are equally likely. And we're trying to find the probability of at least one boy and at least one girl. At least means one or more, right? So there's only 2 outcomes that are inconsistent with that possibility. The outcomes of getting 3 boys and 3 girls, right? All of the other outcomes have at least one boy and one girl, right? So we're looking at 6 outcomes that have at least one boy and at least one girl out of 8 outcomes total. Okay. So this probability would be 6 out of 8, which reduces down to 3 out of 4. Let's look at another example. Let's say that a coin is flipped and then a die is rolled. So we want to use a tree diagram to find the probability of getting heads on the coin and an even number on the die. So let's use a tree diagram to come up with our sample space. So the coin will land on either heads or tails. So we'll do 2 branches for the coin. We'll label those HT, right? So this represents the coin. And then there are 6 possible outcomes for the die. So from the endpoint of each of the first 2 branches, I need to put 6 branches coming off. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. This is the die. And then 6 down here as well. 1, 2, 3, 4, 5, 6. So again, tracing through all the outcomes, I get my sample space. So I can get H paired with a 1 on the die, H paired with a 2, and so on, right? So I would get H1, H2, H3, H4, H5, H6, and then I've got T paired with 1, 2, and so on. 3, 4, 5, 6. So I have 12 possible outcomes in my sample space. And we're asked to find the probability of getting heads on the coin and an even number on the die. Okay, so let's put that over here. My probability will be a fraction. The denominator of the fraction will be 12 because there are 12 outcomes in my sample space. The numerator will be the number of outcomes that correspond to heads on the die and an even number, heads on the coin and an even number on the die. So let me just circle those. That would be heads 2, heads 4, heads 6, right? 3 possible outcomes. So it's 3/12, but that reduces down to 1/4. Okay. Now, in constructing tree diagrams, not all branches have to be the same length. For example, suppose 2 players, Alice and Diego, are matched up in the final round of a chess tournament. And the first one to win 2 games wins the tournament. So the tree diagram would look like this, right? So you have to win you have to win 2 games to win the tournament, right? But the tournament is there's 3 games total, right? So it looks like something like this. The first game could be won by either Alice or Diego, right? The second game could be won by either Alice or Diego as well, right? But if Alice wins game 1 and game 2, the tournament is over, right? Because it's whoever wins the best of 2, right? But if Alice wins the first game and Diego wins the second game, then they have to play a third game as a tiebreaker, right? So here's this. And then similarly, if Diego wins the first game and the second game, the tournament is over. But if Diego wins the first game and Alice wins the second game, then they have to have a tiebreaker round. Right? So not all the branches are the same length in this tree diagram. And my outcomes would be if Alice wins 2 games in a row, or you could have Alice wins followed by Diego wins followed by Alice wins, or you could have Alice wins followed by Diego wins followed by Diego wins, or you could have Diego wins followed by Alice wins followed by Alice wins, or you could have Diego wins followed by Alice wins followed by Diego wins, or you could have Diego wins 2 in a row. Okay. A word of caution here: when the branches of a tree diagram are not equal in length, the outcomes are not equally likely, even if the probability of every individual trial is 1/2. In the tournament example above, if each player is equally likely to win any given games, then the outcomes AA and DD both have probability 1/4, because it's 1/2 times 1/2, while the other outcomes all have a probability 1/8, because it'd be 1/2 times 1/2 times 1/2, or 1/8. Okay. So we can't use this list of outcomes to compute a theoretical probability, because the probabilities, the likelihood of these outcomes occurring is not the same for all the outcomes. Okay, let's turn our attention toward the other tool for finding a sample space. Another way of determining a sample space is by making a table of outcomes. Consider the sample space of selecting a card from a standard deck of 52 cards. The cards are assumed to be shuffled to make sure that the selection occurs at random. There are 4 suits: hearts, diamonds, spades, and clubs, and 13 cards of each suit, consisting of the denominations ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then 3 picture or face cards: jack, queen, and king. So the sample space is shown in this figure right here. Right? So what we have along the top row are the denominations: ace, 2, 3, 4, 5, 6, 7, 8, 9, 10, jack, queen, king. Along this column on the left, we have the 4 suits: hearts, diamonds, spades, clubs. Right? So for each individual denomination can be paired with a suit: ace of hearts, 2 of hearts, right? 2 of diamonds, 5 of clubs, so on and so forth. So we can use this table, which illustrates the sample space, to compute probabilities. Let's say that a card is drawn from an ordinary deck. Use the sample space shown in this figure to find the probabilities of getting a jack, the 6 of clubs, a 3, or a diamond. Okay? So let's take these one at a time. A jack. Well, there are, in a deck of cards, there are 4 jacks, right? And there are 52 cards, right? So this one is fairly straightforward. probability of Jack is equal to 4 out of 52, and that reduces down to 1 out of 13. Okay. B, the 6 of clubs. There is only one card in the entire deck that is the 6 of clubs. It's this one right here in my sample space, right? So the probability of selecting the 6 of clubs, okay, probability of 6 of clubs that is just equal to 1 out of 52. Okay. All right, and then C, what is the probability of getting a 3 or a diamond? A 3 or a diamond. Okay. If you look at my sample space, this row right here is all of the diamonds. Right? This column is all of the 3s. There are 4 3s and 13 diamonds, but there is one card that is both a 3 and a diamond, the 3 of diamonds, right? So I can't just take the 4 3s plus the 13 diamonds and add those together, because I would be counting the 3 of diamonds twice. I don't want to do that, right? So there's really 16 possibilities of drawing a 3 or a diamond, right? Because one of the cards fits into both categories. So the probability of 3 or diamond is equal to 16 out of 52, which is equal to 4 out of 13. Okay, this next example, we go over how to build a table to illustrate a sample space. So we want to use the fundamental counting principle to calculate the number of outcomes for the experiment of rolling two 6-sided dice, and then build a table similar to the one that we used for the card example that illustrates the outcomes for that experiment. Do you get the same number of possibilities? Okay, so for my solution, part A, there are 6 different outcomes for the first roll, and there are 6 possible outcomes for the second roll. So using the fundamental counting principle, we get 6 times 6, which equals 36 possible outcomes. So that's the answer to part A. B would be building the table to actually illustrate the number of possible outcomes. To do that, we could do a column. Let's just do something like this. So up here, we would list the outcomes for the first die, which would be 1, 2, 3, 4, 5, 6. And then vertically down, we would list the outcomes for the second die. 2, 3, 4, 5, 6. Okay. And then inside the body of the table here, I would just take each value from the first die and pair it with a value from the second die, right? So like, let's write these as ordered pairs. This would be 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. Down here we would have 1, 2, 2, 2, 3, 2, 4, 2, 5, 2, 6, 2. I'll put in maybe one more row. So this 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3, and so on, right? So you get the idea. I'm just pairing each value here with the corresponding number down here, right? So if I chose one outcome here, go vertically up to the top, this represents the first number in the ordered pair. Come over here, that's the second number in the ordered pair. If I were to fill out the remaining 3 rows with the same format, notice that each row has 1, 2, 3, 4, 5, 6 outcomes, and there are 6 rows, right? So 6 plus 6 plus 6 plus 6 plus 6 plus 6, that adds up to 36, right? So yes, the table gives me the same number of outcomes as the fundamental counting principle right here, okay? You know what, let's actually go ahead and fill in the table because we're gonna use it for the next example. It won't take that much time. So this is 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 4. 1, 5, 2, 5, 3, 5, 4, 5, 5, 5, 6, 5. 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6, 6. Okay. When 2 dice are rolled, find the probability of getting, for part A, a sum of 8. Let's do this up here. Okay. So how many different ways could we get a sum of 8? Looking at our table, right, I see the top row, nothing there adds up to 8, but the button down here I've got 6, 2, so there's one. Then I've got 5, 3 right here, there's another one. So there's 2, 4, 4 right here, there's 5, 3, 5, that's 6, 2, 6, that's 7, right? And okay, so there should be, yeah, so there's a total of 5 ways, right? 5 ways to get a sum of 8. 6, 2, 5, 3, 4, 4, 3, 5, and 2, 6. So there's 5 ways to do that. So we'll just say probability of sum of 8 equals, there's 5 ways to do that, and there are 36 outcomes total. Okay. Part B, the probability of doubles, the same number on each die, right? There are 6 ways to get doubles, right? We've got 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. 6 ways to get doubles. Six ways to get doubles, and there are 36 outcomes total. So that is 6 out of 36, which reduces down to 1 out of 6. Okay. And the last question, what is the probability of getting a sum less than 5? Probability of sum less than 5. Okay. So a sum of less than 5 means either a 4 or a 3 or a 2. So how many ways can this occur, right? Sum less than 5. Maybe for this one, I'll just kind of circle those outcomes, right? So there's one, there's one, there's one. 2 plus 1 plus 2 is 3. 2 plus 2 is 4. 1 plus 3 is 4. That's it. 1, 2, 3. Is that right? 1, 2, 3, 4, 5, 6. Right? Yeah. So there are 6 ways that we can get a sum of less than 5. Right. So 6 out of 36. It's the same as the answer to part B. So that's also 1/6. Okay. So hopefully that was helpful. Again, tables and tree diagrams can be really useful tools for helping us to identify the sample space, especially for slightly more complicated probability experiments. So we'll stop here. Thank you for watching.